All right, now we're talking about chapter 3, section 2, which is the derivative as a function. All right. So the last section we saw that the first derivative was actually the limit as h goes to 0 of our difference quotient. X sub 0 plus h minus f of x plus 0 over h. That's what we saw. It was the first. So let's define the derivative. Definition of derivative. The derivative of the function f of x with respect to the variable x is the function, the derivative of the function f with respect to x is the function prime at x. What that means is so instead of this one here, we now rewrite it as the function f of x. So this is read f prime of x. That's how it's read. This equals the limit as h approaches 0 of our function f of x plus h minus f of x over h. This if it exists, and the domain, the domain of f prime of x is less than or equal to that of the original function. The domain, all the x's of the x's that are possible in the domain are less than or equal to the same ones that are the original function. Why is this? Is because every time we take a derivative, the function gets smaller and smaller, smaller. So each time the domain of the function is more restricted. The best thing could be is all real numbers, then we get more and more restrictive. Let's see where. I didn't print out the example sheets here, so we're gonna have to do the examples on this thing. Example 1. Differentiate f of x equals x over x minus 1. When we say differentiate, take the derivative. That's what it means. But now, let's talk about what it means. If a function is differentiable, that means you can take a derivative of it. if you can take a derivative of it, that means it has to be continuous. That's important. So a derivative has to exist only if the function is continuous. So differentiate this function. What do we, okay, when we say differentiate, what do we have to do? What are we looking for? So we're looking for the derivative. When we're looking for the derivative, we want this. So this is what we're talking about. So we have to find, we have f of x. We need to have an f. Let's put it here. We need an x plus h. So it's x plus h on top. And what do we have on the bottom? Right. So to find our derivative, take the limit as x approaches 0 of our first function, which is f of x, or x plus h divided by x plus h minus 1, minus our original function, which is x minus 1 over x, all over h. We have to get a common denominator, yes. Limit as h approaches 0. So in this first one, this one has an x minus 1, this one doesn't. So it needs an x minus 1. The second one does not have this x plus h minus 1. So it needs an x plus h minus 1. So we have a common denominator of x plus h minus 1 times x minus 1. On the top, we have an x plus h times x minus 1 minus x plus h minus 1 in brackets, all over h. This is going to get ugly really quick. So what we have to do here is FOIL these two. That gives us x squared minus x plus xh minus h minus, this is after the minus, so I need to keep this in parentheses, So I don't need parentheses inside here, so x times x makes it x squared. Plus xh minus 1, or minus x. Well, we have to first, let's get rid of the parentheses. X plus h minus 1, x minus 1. So we have x squared minus x plus hx minus, change all the signs. So it'll become negative x squared, negative hx, positive x. Well, x squared cancel and positive x. So on top, all we have is negative h. We have fraction over a fraction. So take the top fraction and leave it alone. Multiply by the flip of the bottom. We have negative 1 over x plus h minus 1, x minus 1. So now when we take the h goes to 0, when this goes to 0, that takes care of the. So what we have now is x minus 1 times x minus 1. Our first derivative is negative 1 over x minus 1 squared. It never asks for a point. So this is just the derivative. This is our answer. It will be, yeah, they'll give you most trouble. Oh, yeah. Oh, yeah, anywhere along the way. What I see most often with students is signs. Because whether it's positive or negative, you'll change signs. So, yes. And whenever you do that, never do the work on the same paper. Because you will subconsciously look at that and get confused again. Yeah. Don't do that. Okay, let's look at another example. Example 2. All right. This first part. Find the derivative of f of x equals square root of x for x is greater than 0 And then find the line tangent to the curve y equals radical x at x equals 4. So part A, find the first derivative. Right, the first derivative is the limit as h approaches 0 of f of x plus h minus f of x over h. So we have f of x. That's the square root of x. We need x plus h. There. The square root of x plus h minus square root of x divided by h. In chapter 2, whenever, because if you think about it, when x goes to 0, h goes to 0, we have h goes to 0, that's 0 on the bottom. What do we have on top? It's 0 over 0. Whenever we have 0 over 0, and we have a radical up on top, rationalize the numerator. By the conjugate. That's what we did in chapter 2. So on the bottom, we have what about the top? We have to now FOIL. So it's x plus h. Then it's plus this. Then it's minus the same thing. Negative x. So the middle terms cancel. What else cancels on top? The x's cancel. So we have a positive h over h times radical x plus h. Yeah, the h's cancel, so we have 1 up on top. No, because it was originally positive, x plus h times x plus h is positive. Oh, on the bottom, I'm should be positive, I'm sorry, yeah. I wasn't finished yet. Yes, it's positive. Good catch, good catch. Now what? Plug in zero, so that goes to zero. That takes care of that. So my derivative becomes 1 over radical x plus radical x, 1 over 2 radical x. Where's the question? Oh, there it is. So, because yeah, that's, remember, we said our condition had to be x is greater than zero because you can't equal zero on the bottom and it can't be negative inside the radical. So check. So that's part A. Part B, it says find the line tangent to the curve. Line tangent at x equals 4. Ready? Did I go 2 sides or go 1 side? One side. So what we have here is this for part B. We know the derivative is 1 over 2 radical x. It wants us for x equals 4 tangent line. What do we do first? Remember, the slope is the first derivative. So we need to know the slope. So we put in 4 for x. Right. So our slope is 1/4. So to find the line tangent, we need a point. We know that f of x equals square root of x. And we know that x equals 4. Remember, we need a point. We need an x, y. Well, we have the x. What's the y? Yeah, just plug it in there. So f of 4 equals square root of 4, which is 2. So our point is 4, 2. And our slope is 1/4. How do we find the equation of the line? The equation of the line at 4, 2 with m equals 1/4. Well, how do you find that? We could just go ahead and just plug it into the point slope formula. Since we're given a point and a slope, plug those in there. So this is x1, this is y1. So y minus 2 equals 1/4 x minus 4. Then what do you do? For simplicity purposes later on, whenever you have equal signs and fractions, you have equal sign and fractions. Get rid of the fractions. And here's how you do it. Step one, find the LCD. What's the LCD in this equation? What's the only denominator? The bottom number. Multiply each term by the LCD. Each term, that's a term, that's a term, and this is one big term. So 4 times y minus 4 times 2 equals 4 times 1/4 x minus 4. I multiplied each term by the LCD. Reduce. So there's nothing. This 4 and this 4 cancel. So there's nothing in front. So I just have that 1 doesn't do anything. Multiply to remove parentheses. 4 times 2 is 8. 1 times x is x. Positive, negative, it's negative. And then solve. Yeah, so we add 8 to both sides. So 4y equals x. Since 8's bigger, the answer is positive. 8 minus 4 is 4. Divide everybody by 4. And there's your equation. Equation of the line tangent to f of x at x equals 4.
I thought it was like for I mean, is it the same?
What's that?
I mean, it's almost the same, right? But 1/4 x x for it's 5/4.
Well, yeah, same thing, because there's a coefficient of 1. But this way, I know what my slope is. I know my slope is 1/4. I know my y-intercept is 1. Yeah, so we just have to find the slope first. And this is going back to algebra, because we find the slope, then have a point, find the slope, and find the equation of a line. Next, let's talk about notation. How can we represent derivatives? Mhm.
I just I just try to do. Is it easier to do the other way, like just do 1/4 by 1/4 times x minus?
In this example, it would be. But what if you had other factors that weren't Because what if you had something in front of X, a coefficient in front of X? This is the most easiest all the way around. Because if you didn't, if you had a lot of fractions, then you'd spend a lot of time to figure out LCD. This way, there's no worry. You get rid of the fraction and work it out, and then the answers will become fractions at the end. So as I'm saying, you can use whatever method, but this method here gets rid of fractions, so it's much easier to work with, and then it'll make the answers easier. But yeah, you can do whatever you want to. I'm just showing you the way I always do it.
That's the way I use it. So that's why I never
It is, well, for example, what if you had an equation that was yeah, I mean, in the real world, you have a bunch of fractions. Yeah, anytime you move anything, you have to now worry about multiplying and canceling and finding LCD. This way, if you first find the LCD, get rid of the fractions, you don't have anything to worry about. It makes life much easier. Okay. We learned this. We're going to find other ways of writing this that people use that makes it much easier to distinguish. This means the same thing. dy dx, that means derivative also. df of x over dx. d dx of f of x. The derivative of f of x. The derivative of x of f of x. These are all mean the same thing. You got it? But now, when x is defined as a value, we can have f prime of a or y prime of at x equals a, or df of dy over dx when x equals a. d4 of f of x, or you leave that as x and just put x equals 4, because this says it's much safer to leave it as x, because this tells you that I'm differentiating with respect to x. Because later on, we'll look at we can have differentiate with respect to x and y. So this line here just tells us this is now you have the differentiable. What is the value of x? Okay, let's look at another example. No, we'll combine these later on. The graph of a derivative now that's why I'm going to combine both of these with this example. Graph the derivative of f of x equals, what was that function? f of x. I lost the function. Well, let's make it one over x. Oh well. So we know what this function looks like. The derivative of this function, which we worked out already, was -1 over x squared. What does -1 over x squared look like? Well, first off, let's forget the negative right now. 1 over x squared, it's all positive, so it has to be in the second and first quadrant. So these will be, since it's negative, it's going to be in the third and fourth quadrant. The way you can do it is once you find the derivative, start plugging points in there. So yeah, so we know that we cannot have 0 on the bottom. So x cannot equal 0. And then what we have to do, for example, here at 1, what's the slope at 1? Yeah, so here would be -1. So at 1, the slope is -1. So we put a dot there. At -1, our slope is -1. So at -1, at -1, -1, we put a dot there. At 2 and -2, at 2 we have, so at 2, it's -1/4, which is right here. And then at -2, it's -1/4. So once you find the derivative of the function, just plug in points and there you have it. It's very interesting because it doesn't match the original graph, but each point, this is the slope at x equals 2. So at x equals 2 here, we'd have 1/2. That's the location of this point. The slope here is -1, is -1/4, which is going down. This is a very interesting way of looking at it. All right, let's see what else we got to do in this section. That's pretty much it. Let's look at differentiability on an interval. Differentiable on an interval. Whenever we're talking about intervals, we have to look at one-sided derivatives. Let's say that f of x is differentiable on an open interval a b. This means that there is a derivative at every point or every interior point of AB. So if something is differentiable on an open interval, that means everything inside there is differentiable. But what about if we had a closed interval? How do we do that? To be differentiable on a closed interval, the function f of x must be differentiable at every interior point of AB and at the endpoints A and B. Why does this cause a problem? Because if we have a function and it's differentiable at every point inside there, that means we can take a limit at any point from both sides. Remember, as we defined, the limit to exist has to be able to go from both sides. But if we have endpoints, so at A and B, we need to take one-sided limits. So at x equals a, we have the limit as h approaches 0 of our function. Well, we do at a since we're dealing with a. And it has to exist where? Coming in from the right. Why does it have to come in from the right? Because A is the left side. The only way we can approach A if we're between A and B, the only way we can approach A is from the right.
Oh, it's close, it's close.
Yeah, it's a closed interval, yes. So at B, we have the limit as H approaches 0 from the left of f of B plus H minus f of B at H. So both of these are derivatives. They have names. Because we're approaching H of 0 from the right, this is called a right-handed derivative at A, because we're coming from the right. The other one is called a left-handed derivative at B. Oops, there. All right, let's take an example. Example 4 says, show that the function y equals absolute value of x is differentiable on negative infinity to 0 and on 0 to positive infinity, but not differentiable at x equals 0. Example, yeah. So why do you think? Show that the function y equals absolute value of x is differentiable on that, the left side, negative infinity to 0, and on the right side from 0 to positive infinity, but not differentiable at x equals 0. This was pretty tricky because remember, if it's differentiable, that means a derivative exists, right? So we're looking at f prime exists. Let's do A. This is left side. And then f prime of B exists. This is the right side. What are the formulas for the limits? And then likewise on this side. Oop, the limit as h approaches 0. This is h approaches 0 from the right, and this one's h approaches 0 from the left. Remember, this one's coming in from negative infinity to zero. This one's coming in from zero to positive infinity. So what's the slope? Remember, this finds the slope. What's the slope of the function coming in from the right or from the left? Hmm? The absolute value of x, the formula for it always equals a positive x. So no matter what you give it, positive x or negative x, if I get rid of it, it's positive x, the slope on the left-hand side, the graph of it. On the left side, what's the slope, positive or negative? So it's negative x. And this side is positive x, which is, and the slope is 1 to 1. So the slope is here, it's negative 1. Here it's positive 1. See the problem? They're not approaching the same value. So it's not at zero, it's not differentiable because the slopes are reaching different values. Which use that example. Okay, yeah, I'll use this example. Example 5. Find f prime of x of at x equals 0. Okay, good. Let's find f prime of this function at x equals 0. Yes, we did. There you go. Remember what we got?
One. Yeah.
But we can't go that far because we have to now put x equals 0. So we did. So we have the limit as h goes to 0 of x plus h minus remember x is 0. So we have 0 plus h minus 0 over h. So we have square root of h minus 0 over h. Well, let's look at this. We can simplify this even further. This is equal to x or h to the power 1/2. This is h to the power 1. Whenever you have the same bases on the top and bottom, you subtract the exponents. So there's half on top, one on the bottom, so we're left with half on the bottom. Which is square root of h. As h goes to 0, what happens here? It goes to infinity. Because remember, you can't have 0 on the bottom. If 1 over 0, 0 goes into 1 infinite number of times. So it's undefined. It's undefined, but it's infinity. So that's what we're looking for here.
Not, the same person that gave it last time. Why is it the excess in before the created because last time we did it after.
We did it after, yeah. We were first going to find out what the value was. The thing about it is this function, we typically look for it when x is 4 or something. Very rarely do we look for the end point. At the end point, what is the slope there? Well, because we know it's infinity, it's a vertical slope. So in the other ones, we always ask for values outside of that. But this time we're going to look at, we could have waited to the end, but if we did to the end, then we would have lost all our h's. Because I want to do this before we lose our h's. No. Is that example 4 or 5? 5. Okay, now let's look at where do functions not have a derivative? At a point. There are 5 places. 1, corners. So if you have a piecewise defined function and you have a x squared here and this is like negative x, at that point, not differentiable at that point. At a cusp. Right here, it's not differentiable. A vertical tangent line. There. And later on in this course, we're going to give that point a name. A discontinuity. and a wild oscillation. If it sporadically really fast goes up and down really fast in a short amount of space, again, wild means between a very small segment, it may have 100 maximum minimums because it occurs so frequently, you don't know what it's going to be. So these are the 5 conditions where a function does not have a derivative at a point. Basically, at points, you cannot have at points at pointy places where it's a point, a sharp point at vertical lines. The reason that's a vertical line, because here you have the curve is going down and then it starts going up. At this point here, the slope is undefined. At discontinuities and then at oscillations. Those are the ones. So, as I've said before also, in order for a function to be differentiable, it has to be continuous. So differentiability implies continuity. Differentiability implies continuity. In other words, if a function is differentiable, then we know it has to be continuous. Can we say the other way? Can we say if a function is continuous, it has to be differentiable? Why not? Continuity does not imply differentiability. Let me give you a hint. Look up there.
Oh,
These are all continuous functions.
yeah.
But it is right there in front of us. Yeah, that's what you have to, because there will be some times in this course where we have to make sure the function is continuous before we go any further. In other words, if it's continuous, then we can know we could try to take a derivative. But if we can take a derivative, then we know it has to be continuous. Okay, that does it for today. That's the first 2 sections of chapter 3. What's that? Oh, yeah. Oh, from here on out, the rest of this chapter will actually, to be honest with you, the rest of the course will be much easier because it's going to be just using formulas to do this stuff.
Yeah, it's for me, it's still that
Yeah, actually, I have to redo those. I have to do 2.3, I believe, because I messed it up. I didn't record it. So there it is. From now, even what we did today, finding the limits of taking the f of x plus h, that's way too much. That's too much work. We're going to learn something in the next couple of sections where this is dinosaurs compared to what we're going to do. So imagine doing a derivative. Imagine doing this x plus h 7 times. X plus h times x plus h times x plus h. That's going to be way too much. So we have to come up with shortcuts. That's what's next to on our agenda. Yes, because we're gonna learn much faster ways to do this. It's gonna leave everything else in the dirt. All right, guys, have a great day. I'll see you Wednesday.